Hello everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm your host for today's presentation, and we're excited about having a new presenter joining us this week. Before I introduce Kyle, as we are in the habit of doing, we'd like to start with a couple poll questions to get a little bit of a perspective on the audience's approach to the topic. So if you would please help participate by responding accordingly. So the first poll question is, how often do you have to mitigate arc flash incident energy in your projects? So again, there's no obligation or liability. It's strictly just trying to get some feedback on the audience's activity in this area. Just as a housekeeping note, after the webinar, we will supply via email an attendance certificate that most people use to support their continuing education credits. So you don't have to do anything from that, but you do want to make sure we got your correct email address. So it looks like we have a quorum on this question. Let's see how everybody responded. So it looks like pretty heavily split between the haves and the have-nots. Second question is, how often do you use secondary relaying for arc flash protection? And again, this goes more to the heart of the matter for today. We will try to leave some time at the tail end of Kyle's presentation for questions, but by all means use the question control box in the GoToWebinar pane to enter your questions at any time. Here's how folks are responding to this. Good. Thank you. And then finally, are you familiar with Eaton's VFI capabilities? And the nice thing about the presentation, it gets into a lot of detail of the nuances of calculating instant energy in this part of the circuit. So I look forward to the presentation myself. So that's a quorum. Let's see how people have responded. So it looks like everybody's ready, willing, and able. So thank you for participating. And at this time, I'd like to hand the baton off to Kyle Zamanovic, who is our guest presenter today. Kyle, you have the baton.
All right, thank you, Jim.
Okay, I'm looking.
All right, can you
PowerPoint slide? Yeah. Perfect.
All right, awesome, thank you. Yeah, so my name is Kyle Zamanovic. I'm an application engineer with Eaton, with the Cooper Power Systems division in the liquid filled transformer group specifically. Today, I'm going to be talking about our arc reduction vacuum fault interrupter, or for short, AR-VFI transformer. So I'll be saying AR-VFI transformer quite a bit to shorten that up throughout the presentation, and really talking about how it enhances the arc flash safety on the the low voltage side of the transformer down to low voltage main breaker or so forth. So to start off, I'll first talk about the IEEE 1584, the initial 2002 edition, and then some of the updates and how they are impacting our systems today and some of the new models in the 2018 edition. And then also talk about some of the OSHA electrical safety requirements in regards to PPE. And then we'll do some case studies, jumping into some of the traditional fusing where it's just primary protection, and then some of the modern methods of incident energy reduction, and then some of the key components that are used in that in those models, and how we integrate that into one product, which is our AR-VFI transformer, and those different key values and applications. Okay, so in terms of arc flash zones, the rule generally is that if you have some type of equipment, whether it's transformer secondary or a piece of low voltage equipment that has more than 40 calories per centimeter squared, it must be de-energized, and you are not permitted to work on that per OSHA. And honestly, I would say no one really wants to work on that. That's some extremely dangerous levels of energy. And although there may be some PPE out there, that goes to 40 calories or 100, calories. That's really great for a fire resistance nature, but not really an arc blast, so that physical concussive force that you might see from some of the arc flash events. And a much better way to address that rather than wearing PPE is to look at how we can actually mitigate these high energy levels altogether and make it a truly safer piece of equipment. So we'll jump into the comparison here of the 2002 edition of IEEE 1584 and then some of the differences in the newer updated version in 2018. So the 2002 edition included 300 different tests used to develop the standard, and overall was a good standard. It's a good leap into how we interpret and model incident energy in all sorts of different gear, but it was really just a one-size-fits-all answer at the time for different types of gear. So you would use like a similar model for a transformer secondary versus a three-phase panel board, a piece of just general low voltage gear. And then in 2018 is when the newer version of the standard came out, including an additional 2,000 tests. And this included quite a few different parameters and variables into that new model that we use, and really drives the differences we see in the different types of gear. So the two main changes I really want to focus on is the third from last there, the enclosure size correction factor, and then the last one listed the electrode configuration. That first one, the 2002 edition, had no distinction made for enclosures, versus the 2018 standard has a correction factor included for voltages and as well as for the shallower, what they call a typical depth of the enclosure. And you can kind of think of the enclosure of a little bit like a backboard or even like a barrel of a gun, where the arc energy is going to push outwards towards the user compared to where there is no enclosure and it won't be pushed out in any specific direction. And then that goes right into describing the electrode configuration, which is the layout of those three-phase buswork that you have, and whether it's in the gear or in the transformer. All right, so focusing on those electrode configurations, up on the screen we have 5 different configurations that the IEEE team came up with. And in the 2002 edition, pretty much everything would fall under that figure 1 category, the VCB standing for vertical electrodes in a box. Again, it's a good middle of the road sort of value, where that included a lot of different pieces of gear. But what the IEEE team did find is in making these new configurations that were in some cases the energy was less, and then in the 2002 model, but in some cases it was quite a bit worse or higher energies than what they initially thought. So if you look at figure 4 and 5, VOA and HOA, which stands for the vertical or horizontal electrodes in open air. This may be more common for an open style substation transformer, something with like cover mounted bushings, where potentially the arc will be less likely to happen, or just it being that style of unit really doesn't have anything to contain that arc energy and propagate it towards the user. In that case, it might actually be a little bit better of an energy value than what we initially thought in those 2002 models. The energy might be a little bit less. But in the other hand, if we look at figure 2 and 3, I know we got figure 3 highlighted, but I'll get to that in just a second. But the VCBB and HCB orientations, those can actually be quite a bit worse. So the VCBB can be very common as like a model of a 3-phase buswork, coming down into a molded case circuit breaker or something where you have your 3-phase conductor going down into a non-conductive insulated surface. And with the HCB actually ends up being the worst case scenario. You might think this looks similar to a transformer secondary, your low voltage bushings, where you have your them pointing outwards from the side of the tank or the front plate horizontally. And they would be facing towards the user when you're standing in front of the enclosure. And what we find with this HCB comparatively to the 2002 edition, the values are roughly on average 190% the energy we would have presumed with the earlier 2002 model. So this means that if you were at an energy level of, let's say, around like 20 calories per centimeter squared in the 2002 model, you would actually be closer to 40 calories, which puts you into that zone where normal PPE would be not suffice, or there's no PPE available. And I'll get into that in the next slide in a little bit. But one thing I do want to point out here is that the energy has not gotten worse as time went on. The energy has always been present, and we're now just better understanding how to model it. So how that arc propagates and how its energy really goes towards a user depending on your electrode configuration and your enclosure. So this is something that is being used by a lot of people now to update their system and doing new studies to better understand what kind of energy is really in their system based on this new model. All right, so looking at how OSHA considers the PPE categories and how they look at those energy levels that I was just referring to. So calories per centimeter squared is that incident energy on the surface area of whatever that three-phase buswork is, whether it's the spades of the transformer or a general bus. So as far as OSHA is concerned, their category energy levels did not change from the 2002 to 2018 edition. Those pieces of personal protective equipment were tested to those specific values, and those values still hold. But as I was stating, we're now better understanding that we may have under-predicted the amount of energy present in some of those cases, especially with the transformer and the switchgear. So with that, you're typically targeting like a level 2 zone where you're just wearing gloves and a face shield. That's typically what our customers are targeting due to the ease of maintenance, and where you're just slipping on the gloves and the face shields compared to level 3 or 4 where you're having to dress up in that big moon suit there. I've spoken with customers before, and some facility managers may opt in to say, let's just get everybody a 100-calorie suit. That will cover everything up to 40 and then some, but you're also putting your personnel in this big moon suit can increase the chances of making an error and could cause an event, and all that energy is still there. So really targeting that level 2 or less is what prompted the push for more advanced technology to be built into something like the transformer, which we'll talk about in some further slides. And it's not only for the worker, but also for the equipment longevity and preserving your equipment in the system there. And as far as OSHA is concerned with de-energization, anything above that 40-calorie mark must be de-energized for work and is considered inaccessible. So you can see I got that red square on the right there with the big X over it. We wouldn't argue with the de-energization as a good solution, right? I mean, when possible, that is definitely a great option. However, there are a lot of applications where they do not have the option to shut down that equipment that requires them to work on it live then, and then it puts themselves at risk. So all the more precedence to have this type of integrated technology to offer an overall safer solution, or safer system, I should say. All right, so taking a look at a very typical secondary of a pad mount transformer. So we're looking at the front plate with the high voltage and low voltage compartment doors open. It is very common to have accessories located in these compartments. So you got your nameplate over there with all the transformer information, the KVA, the voltages, the part numbers, things like that, along with your gauges right there next to it, things like your temperature gauge, pressure vacuum gauge, liquid level, things that you might commonly go and check on for maintenance. You also have your drain and sampler valve in the bottom of the low voltage compartment. If you want to go and get a sample of the oil for DGA analysis, you would have to get access to the low voltage compartment, which is usually located behind some of the low voltage cables there in a typical configuration. And then on the high voltage compartment side, you also have your bayonet fuses and load break switches or sectionalizing switches. And all those things are very close to what we call the secondary arc flash hazard zone there, highlighted in yellow. So per IEEE, you have to open the low voltage compartment door first to even get access to the high voltage compartment. So if you wanted to de-energize the transformer first, you would have to still open that low voltage compartment door first. Things like the switching and also changing the fuses. And if it's not de-energized, then you're very much at risk and being exposed to very high energy levels. And really pretty much anything above a 300 kVA or so, depending on what that secondary voltage is, exceeds that 40 calorie limit, meaning it has to be inaccessible unless de-energized. And some people may think, why would I even need to get into the transformer secondary compartment? You know, there are solutions like putting the gauges or nameplates and things like that on the outside of the compartment. And, you know, I wouldn't argue with that. You're removing people away from that arc flash zone is always a great solution. And it's also obviously a cheap solution as well. But maybe you're not trying to get into the transformer. There could be cases where you're trying to get into the downstream piece of, let's say, service entrance switchgear. And if you're taking 50 calories out of the transformer secondary, you're also taking that same energy out of any of that gear, that low voltage gear downstream as well. Okay, so now I want to jump into some case studies here. So we'll look at a couple different ones. It's really a combination of traditional technology as well as case studies where we're doing some of the modern arc flash or reducing the arc flash energy for protection. So we'll start out at looking at a commercial bottling facility where they were looking for a robust solution that worked from an always-on solution. So I'm sure some of you are familiar with a maintenance mode, or what we would call ARMS at Eaton. And there are ways to enable tighter settings, but temporarily. So they are good solutions, but typically suffer that key piece, that is that it needs to be activated in order to work or be enabled. Something has to trigger to turn that setting on. So this customer very much needed an always-on solution that was protecting their gear and their personnel, even if something like maintenance mode was not switched on. All right, so then taking a glance at this single line diagram for this case study, the primary protection normally is a pole-mounted vacuum recloser followed by the standard pad-mounted transformer. And in this case, it had secondary CTs mounted on the bushings. And that's feeding a downstream transfer switch with 5051 relaying. In this case was a DT3000. All right, so in this case, we're looking at the two scenarios, right? So looking at the open transfer switch or this piece of draw switch gear, we're going to be looking with and without that secondary relaying and the secondary CTs, and then with those features back in there and seeing the comparative energy levels. All right, so we're looking at the no relay, no secondary CTs, and we're just relying primarily on that pole-mounted vacuum recloser that's located upstream. And before I go into the values that we're going to see, the primary vacuum recloser in an always-on solution like this must be coordinated with the transformer inrush. So if we look at transformer inrush and damage curve, that damage curve is when too much energy is going through it, that it will damage the transformer. And then the inrush curve represents the amount of current that will be pulled into the transformer during startup. And if we have something like a pole-mounted fuse or pole-mounted vacuum recloser, it needs to be able to ride through that large amount of current that is initially pulled in without tripping in order to really energize the unit. So then it can be on after it rides through that. So the settings have to be loose enough to allow that current to rush in. And you can't have that tight protection in that scheme to give us a quick trip or fast clearing time and low energy. All right, so looking at the situation with no relay and no secondary CTs, just that primary upstream vacuum recloser. Get the values up here. You're looking at about 160 calories per centimeter squared and an arc flash boundary of greater than 20 feet. So that means you have to be at least 20 foot radius away from the potential explosion to be safe in any means. This is over 4 times the amount of energy that OSHA would dictate as something that is accessible or not. So in this scenario, this is something that would need to be de-energized. And in the bottom right-hand corner there, that hazard zone we're talking about, that's from the low voltage bushings down to the low voltage main breaker, whether that's close coupled, further downstream. Obviously those distances can vary based on application. And if we look at that same scenario now, but we're incorporating that DT3000 relay and those secondary CTs located in the transformer, it's not needing to be coordinated for transformer inrush. They're located on that load side of the transformer. So we're not having to take into account that core magnetization. It's just the immediate pickup from the CTs sending their signals to the relay and then back up to the vacuum recloser to trip. So with this scheme, we're able to decrease that clearing time and reduce the energy below 20 calories per centimeter squared. So this is over an 8.5 times reduction. It's important to note this is not in maintenance mode, and there's no instantaneous setting on for this example. This is still in coordination with all the feeder breakers. But you can see now the arc flash boundary is reduced to about 8 feet as well. So it went from about 160 calories per centimeter squared down to 18 or below 20. Okay, so we can go ahead and look at a second case study, and this one is for a wastewater treatment plant that's powering pumps to avoid chemicals from getting into a nearby river. So this is very important from an uptime perspective, where it needs to be in that always-on solution that we were talking about. And in this case, the customer did require less than 8 calories per centimeter squared. All right, so looking at the setup here, in this case, we have a pole-mounted fuse cutout in the green box. Those are utility-owned and not very tightly coordinated. Although in some cases, the utility may be able to work with you to tighten some of those protection settings. It's very often, it's likely feeding multiple customers as well. So it would be using a fuse to avoid nuisance operations, considering all the other customers it might be feeding. So it's more loosely coordinated to be able to handle that transformer inrush. So it will interrupt eventually, but does not have that speed that we were talking about earlier to eliminate some of the arc flash or create those arc flash safe zones, I should say. And then looking at the rest of the gear, in the red box, we have a VFI transformer. So from the last case to this case study, you'll see we're a little bit more integrated, where we have the vacuum fault interrupter located or integrated into the same tank of the transformer, rather than having it separate of the transformer like we had before. You had a vacuum recloser, separate piece of equipment, or you could have a VFI switchgear, but this is completely integrated into the transformer tank. And this also has secondary CTs on the transformer as well. And then the relay is the Eaton EDR 3000 relay, which is in the draw out transfer switchgear just downstream. So we're going to go ahead and look at the single line for this and show some of the comparisons. So we have that switch zone where anything ahead of the low voltage main breaker is what we're looking at. And with the VFI in the transformer, but we're ignoring the, I guess we should say we're ignoring the VFI in the transformer and the secondary CTs for this. We're just looking at the fuse cutouts upstream for the comparison. We're looking at about 34 calories per centimeter squared and a pretty significant clearing time. For those of you that are unfamiliar, the clearing times that are over a second is essentially eternity in arc flash terms. While it does interrupt, it does not get that arc flash energy down and would be unacceptable to the customer. So this was just looking at those fuse cutouts to protect the system. And now we're going to be considering that vacuum fault interrupter, the VFI in the transformer, along with the secondary CTs and that secondary relaying scheme to protect it instead. All right, so that fault is sensed by those CTs much quicker compared to the other, just the upstream fuses doing all the work. And I'm trying to get this to load. Here we go. So that shows that we dropped down to 7 calories per centimeter squared and drastically reduced that arc flash boundary down to 4.3 feet. And then the other thing to note is that clearing time, instead of being, I believe it's like 1.6 seconds or so, is now 0.219 seconds. So drastically reduced clearing time overall. And again, this is not having to worry about that inrush. Since it's located on the secondary side of the coils, it's able to pick up that fault much quicker and send that trip command. So I do actually want to look at a real-world arc flash event example as well. So this is an example where they actually did have a full arc reduction VFI transformer. Before, we were kind of looking at the concept of the secondary relaying and some of those pieces spread out in the system. And this is actually more of a earlier model but for the most part, it's kind of one product. So this case, it has when I say an earlier ARVFI model, I mean that it has a secondary feeder relay, in this case an SEL 751 with our normal tri-phase TPG control on the primary with a vacuum fault interrupter in the tank. And effectively, it's the same as having one single differential relay by having both the primary and secondary pieces for sensing. And in this application, it was a data center, and the customer has actually experienced a few different types of startup issues, and really no fault of their own. But just it's common for issues to happen in this type of application during startup, just because of the different variables and settings, and the system has never really been energized. So the initial startup can be a dangerous time. In this particular case, we had a whole data center lineup where the transformer was feeding both a low voltage gear and a low voltage UPS system. And in that UPS system, I was told there was a small piece of shipping support that was not seen during the initial installation, and it had fallen down and laying across the A and B phase buswork. And it was already lying on the buswork prior to energization, so it didn't fall down afterwards. So all of the gear was closed and ready for energization. And as it was all energized from equipment upstream, is when they had the event happen. Unfortunately, they had the secondary sensing technology, so the ARVFI transformer technology built into their system, and they were able to trip during this overcurrent event at startup in an extremely fast amount of time versus if they had a primary device alone for the protection. So I actually do have those waveforms for that event. So if we look a little bit further, the energization starts right around the node where all three phases are no longer synced up at 0. So that's between like the 260 millisecond, 270 millisecond marks. And then we start to see a sort of a typical A, B, and C voltage waveforms. And right at about 273 milliseconds, you start to get some type of crossover and anomalies where that A and B phase start to spike, which is where we start to see that overcurrent event arcing through that fallen shipping support. It ended up reaching a magnitude of about 33 Ka. And what happened here is just under a quarter of a cycle or so of basically pickup time of the CTs, being able to pick up that overcurrent event and computate that signal through the relay into the actual interrupter, so the VFI, and then opening up the vacuum interrupter in one cycle and then clearing the fault in another cycle. This resulted in a total fault clearing time from the pickup to the fault being cleared in about 2.22 cycles. So that's just over a 30th of a second, an extremely fast amount of time that was able to keep that fault energy at about 1.9 calories per centimeter squared. So well under the level 1 category in this scenario, and no more than just like a small singe on that buswork. So that protection scheme prevented a pretty catastrophic event when it comes to the safety for the personnel at the site, and then also damaging that UPS. And at this point of the project, I mean, it can be pretty difficult to obtain a replacement piece of equipment when you're already in the commissioning phase. So in this case, there's just the singe on the buswork I was mentioning. They just cleaned that up, checked everything, retested it, and they were able to re-energize without having to replace the equipment. And just some highlights on the bulk of what I'm trying to get across to you guys today is that, the primary devices alone, such as a primary fuse or primary vacuum fault interrupter, it will end up leaving this high energy hazard zone between that low voltage of the transformer and that low voltage breaker, as I have highlighted in red in that little diagram. It's a zone that would, eventually be interrupted if there's no arc flash concern, but the fuse, that fuse will operate, but could take a few seconds or so. So it is a slow clearing time type of protection scheme. And if you want to improve that system and reduce that arc flash energy in those zones, something like the arc reduction VFI transformer that we're going through today is where it would really shine. This is where it would be a great solution for that type of scenario. And we already discussed, those different components that contribute to reducing that arc flash energy. So that'd be the CT, the relay, and tripping, the secondary CT and the secondary relaying scheme to trip upstream. And the AR-VFI transformer really takes those crucial components and then that are normally spread out, I should say, amongst different pieces of equipment and integrates it all into one piece, which is that transformer tank. And beyond those safety benefits, because since we're integrating it all into one piece of equipment, one design, it offers other benefits like space-saving opportunities. You're shrinking that overall footprint, and you're, along with the benefits of the simplified installation, you're not having to wait for the lead time of the equipment to show up. Then, obviously you should have the pads poured. You have to pull cable underground. You have to install and connect all your equipment, and then test all your equipment together as well. And then looking at that AR-VFI transformer single line, that hazard zone now that was before from the low voltage bushings all the way down to your low voltage main breaker is now reduced to just your low voltage coils to the low voltage CT, which is actually located under oil in the transformer. So now that hazard zone that was fully external is now limited to just inside of a sealed tank, which essentially eliminates that hazard, that arc flash hazard. And then going a little bit more into that componentry, we talked about all those major components that are proven to work, right? It's something that's been around and been used for a while. But the real question is who takes responsibility for that integration. We know that the primary device is the means of interruption, and the transformers, that's sort of key with that inrush component that you need to coordinate around, and having that secondary CT and relaying can help provide a solution. But there can be a lot of difficulties in the field of actually making all those things happen correctly. So, you have to wire the CTs to the relay, getting that relay, I should say, trip signal up to the interrupting device, supplying power for all those devices. You have to coordinate all the specific settings as well. And then also a big one is choosing the right componentry to work all together properly. But I say the most important one is really that overall system validation testing of it as a whole lineup, and proving that it actually works. I mean, you can test a lot of these things at a component level, but when it's getting into more of a full system test, it can be very difficult to do that in the field. So that's something that Eaton has taken the responsibility of, not only integrating all of this into one product, but also factory validating this and making sure that it's fully functionally tested at the factory before it's shipped to the site. So none of that has to be figured out in the field or at the site. Okay, so we talked a lot about the components and what is essential to help reduce the arc flash energy with the secondary relaying scheme. So now just looking at the actual AR-VFI product itself and what's included with it. So the AR-VFI transformer does have obviously a vacuum fault interrupter integrated into the tank. It is a technology that has been around for 25 years or so, and we've been using it. It was in our switchgear group, and we've also been using it in our transformers now for a while. We have also an incorporated differential relay there. The differential relay really just provides the inputs for the primary and the secondary CTs. So that gives us the instantaneous and the time over current, or the 50-51 protection on both the primary and secondary side. We also have included the primary and the secondary CTs integrated into the tank under oil. And along with that, we also have an integral control power and battery backup system. And this can be something that's usually overlooked. It can be kind of difficult to source the power on site if there's no 120 volt source available to power all the equipment. So including that integrated power into the transformer and the control box is a convenient feature. And then along with having that battery backup or UPS system is really just to ensure that the relay can perform its self-diagnostics and really control the transformer for the duration of an outage. Some of the other optional pieces that aren't always included but can be if a customer requests it are primary PTs for voltage monitoring, along with a motor operator for the remote actuation of the VFI. So that is something that we would mount on the VFI or the external handle, and it would be wired up to the control box and have convenient features for the user to be able to easily re-energize or de-energize the transformer with just the push of the button, and all this being located outside of the main compartments or cabinets on the side of the tank. You also have things like the various external gauges. So you could do the gauges in the transformer external or just leave them in the normal spot, but things like liquid temperature gauge with contacts, RTDs, liquid level gauges, pressure vacuum, things like that, that you're monitoring the transformer constantly, can all be wired into that relay control box that's external of the cabinet, and you can do different things with that, like to wire into a SCADA system of some sort. And again, this is all integrated and factory tested at our facilities. So I did spend some time talking about the clearing times and the incident energy reduction for those case studies, but I do want to just touch base for some examples on the actual ARVFI transformer itself. So in this case, we're just looking at a 1500 kVA with 480 volt secondary, but what we're comparing is the top row there for the traditional primary fusing. So this would just be a standard 1500 kVA transformer with bayonet and partial range current limiter fuses for your protection. And you could see that's about 870 milliseconds. So, approaching that 1 second mark, it's a pretty long clearing time. And then when we go to the next slide, I'll show you how these clearing times translate into increased incident energy or decreased. And looking at the ARVFI, the third one down there, we're below 4 cycles or 67 milliseconds. So a pretty drastic reduction in your clearing time. One of the actual features I didn't talk about, or the options I didn't speak about on the last slide, was arc light sensing. So with our standard ARVFI transformer, not only are you sensing on the secondary side with CTs, you do have the option to include arc light sensors inside the low voltage compartment. And what that would do is help reduce your pickup time even more. So you're down to 3 cycles or so, or 50 milliseconds. So you're able to increase that clearing time even further. It doesn't sound like a big change when you're talking like 4 cycles to 3 or 67 milliseconds to 50. But if we do look at the incident energy comparison, that'd be that the ARVFI standard is the green line, and then with the arc light sensing is that blue line. If you're trying to get a larger kVA or stay in that PPE level of 2, you can almost get up to about a 2500 kVA with still being in that level 2. But for both ARVFI and then one with arc light sensing, you're still in that level 3 zone for 5 MVA and above. And you can be in that level 2 for just the green line, I should say, for just over 1000 kVA. But the big comparison here is that traditional fusing, the red line, where it's already at 300 or 500 kVA, and you're already in that what OSHA would call too dangerous, above 40 calories per centimeter squared, where you should not be operating or accessing this piece of equipment unless it's de-energized. So there's a pretty big comparison here in your overall energy levels. And from a product scope standpoint, we go as low as 150 kVA. We can do it for substation style, which is shown on the picture, or pad mount style. And we can go all the way up to 12.5 kVA. So pretty much any of the 3-phase transformers we make, up to 35 kV and 150 kV BIL. We do offer under oil partial range current limiter fuses, which would be in series with that VFI mechanism. And that's really just to help cover any internal failures that would require that higher interrupt rating. So if you look at the ratings of the vacuum fault interrupter, that mechanism can interrupt up to 12.5 K for the 25 and 35 kV classes, and then up to 16 K at the 15 kV. So if you have energy higher than that, or available fault current higher than that, we can always include a current limiter inside of the transformer to bring that overall interrupt rating up to 50 Ka. So that is one option as well. And then there's also a lot of, the things that we talked about on here, some of the integrated features and benefits of this product. And the big thing that we really want to drive home here is just that there's different ways to do arc flash safety in the low voltage side of your transformer down to your low voltage breaker. But a lot of those solutions do require multiple pieces of equipment that are typically spread out amongst different pieces of equipment, and also coordinated by different groups, installed in the field, tested in the field, programmed in the field, and really taking all of those different pieces and standardizing it into one product that's tested and verified from the plant is the real benefit of the ARVFI transformer. aside from actually, you know, the arc flash reduction and the clearing time improvements. So that was the main bulk of the stuff I want to talk about for arc flash safety and how the ARVFI can improve the arc flash energies. So I guess, was there any questions on what this?
So I put the questions in the chat box.
Oh, there it is. Okay. So that first one, where does OSHA state you may not work on anything energized when it's greater than 40 calories? I'd have to look back on that one. That's a good question. I don't have the specific section on that one. I don't know if Jim, if you have any comments on that.
No, I'm not familiar with the OSHA standing on that.
Okay. I'm just reading the second one. If we reduce arc flash levels on the medium voltage side with help of relays, but we reduce levels of withstand capabilities of system, how do you achieve both capabilities of withstand strength of breakers and reduce arc flashing? Is that talking about like the interrupt rating?
Yeah.
Well, I guess it depends, right? So I think I touched on that at the end, where if we're including the current limiter fuses, I mean, you still have overall protection up to 50 Ka. Although that breaker, the VFI mechanism, let's say in the case of it's only rated 12.5 Ka, if you do have available fault current that's higher than that, realistically, the only time you're ever going to be seeing that full available fault current is if the transformer were to be failing, or have essentially that impedance element of the transformer is gone. So in that case, would be a transformer failure. You're not usually worrying about that switch, and that's why that current limiter fuse that we would include is under oil. It's meant to interrupt very quickly in those high energy faults. So in that case, like a transformer failure, and you wouldn't really want to be easily replacing that fuse. Looking at the third one, when selecting and implementing a maintenance instantaneous mode using an overcurrent relay and secondary CTs, what needs to be considered when selecting the current pickup for the maintenance mode? When it gets into the specific settings, I'd have to pull up what we do as a standard there. Because what I mentioned earlier, when we program these, we aren't using the 87 differential settings. And that's mainly because that zone of protection would only be the inside of your tank. So the primary CT to the secondary CT, so just your core and coil. So that really doesn't have any benefit. And then if we actually include the arc light sensors, you could kind of think of that as speeding up your time with it almost being more equivalent to differential speeds, but we're using that 50-51 protection for your main kind of always on solution. But then when it comes to programming the maintenance mode, I'd have to look at what we typically do for those settings. But I'd be happy to look into that further. So Jim, I don't know if you're giving out my contact information or how we go about further diving into some of these questions, but I'd be happy to go into some of these more in depth with if I'm not able to address them on the call.
We can follow up with a Q&A circular to everybody that attended. Okay.
Vacuum switches are notorious for current chopping, causing voltage spikes. How does Eaton deal with this issue? That's a great question. Yeah, so we're definitely aware with the transients caused from vacuum switches. So one thing that we do is we actually have a white paper on this, and I could try to find that for you guys. It's on our website, but it is about what we call like our critical load transformers, or why you do not, or why they're more built to be able to handle these transients in our liquid filled transformers. So although the transformer is not concerned, so the transformer itself would not be a concern or be damaged by these voltage spikes you're asking about, you do have to be concerned about what's downstream of your transformer. Any sensitive equipment that might be closer located, or isn't further downstream, I should say, could be affected by some of those voltage spikes. But we've mitigated that by standardizing on what we call storm trapper arresters on the low voltage side to help trim some of those spikes out that we could see from the vacuum fault interrupter to minimize any of that on the downstream side of it. And that's usually the big concern when it comes to the vacuum fault interrupter, is, for us at least, is what is downstream of the transformer. So we include standard notes on that information to make sure the customer is aware of those potential risks, but there's a lot of easy ways to mitigate that. Like I said, using those storm trap arresters on the low voltage side. And if you guys want more information I was talking about for the transformer itself, I believe what we have is like a hardened data center is what you could look up, and then we have some white paper topics on how that technology works, or how the liquid filled transformer is built to withstand those type of transients. Approximate increase in cost between 2500 kVA pad mount and same size in ARVFI. That's obviously one of the biggest questions we get. Unfortunately, I'm not able to note on that. I am an application engineer, so I stick to the technical side of it, but it's hard to say what the overall price increase can be. Generally, what we see though is when you look at the big thing to focus on is that total cost of your system. So let's say if you just look at like a standard VFI transformer, without the secondary sensing and everything, you're just integrating that primary switch mechanism into the transformer. Typically what you see is you're saving money on an overall cost of the two pieces of equipment and integrating it into one. And it's not necessarily just looking at the equipment cost, you're also looking at the cost for installation of the two separate pieces of equipment. And then when we look at like the ARVFI transformer, not only you have the separate pieces of equipment, but you also have the engineering time and testing and coordinating and installation of that whole secondary relaying scheme. So although I don't have a percentage increase or a price comparison for you, that is generally what the price benefit of this type of solution would be, is being able to integrate that into one product takes away all those extra costs for separate equipment and installation costs and coordination and testing. Again, the big thing is that when we integrate that all in the transformer, we can drive the component selection. We can make sure everything is kind of engineered to work together well and standardize on that. And when we do that, from a standardization perspective, we're able to actually keep our lead times down on the product to really mimic like a standard three-phase transformer lead time. So going from a standard pad mount to an ARVFI pad mount would have a similar lead time and would not drastically increase, where you would benefit from an overall site installation lead time sense, as you don't have to wait for lead times of the equipment, but then also the lead time of the installation and testing of the whole protection scheme. What is the lead time of this product? I guess I just kind of answered that. So again, I don't know what the exact lead times of our transformers are right now. In general, transformer lead times are pretty long, but this specific product would be similar to our standard transformer lead time. So no increase in lead time for the ARVFI product, to sum it up. Is a 400 amp circuit breaker, I'm not sure what that question was saying there. Or is that just a comment?
I think he's augmented it with something he just posted, so pick it up later.
Okay. How do you coordinate the protection such that a close in-bus fault below the secondary main does not actuate the primary protection? Is directional comparing blocking utilized? It can be. We have, using that relay scheme, you can do a lot of different type of coordination with it and communication. So from a transformer standpoint, coming from our factory, we can only, so we'll program all the settings ourselves for like the primary secondary protection. We know the transformer size and impedance, so we know the optimized protection curves and stuff that we would set in the relay. But if it's coordinating with other equipment downstream, so you don't, if you want to make sure you trip your low voltage gear before you're tripping like your primary breaker, that can be coordinated. We can work with you guys on that. We just need to know what that would be, right? So we can provide you our relay files and what we were doing, and you can always change your settings as well. One thing to note is if we are using a current limiter fuse in the oil with the VFI mechanism, those are coordinated together. And since a current limiter fuse is a fixed, curve, I should say, for protection, we will put a hard, like, engraved nameplate on that control box, letting you know that you really shouldn't be adjusting settings, so that they properly coordinate with that current limiter fuse still. But if we're able to talk about it early on, and your coordination concerns, we can always review that and make sure that we program it accordingly. So the question is, this amperage one, are you saying is 4,000 amps a limit in 408 volts?
Yeah.
So the beauty of this is if you're trying to use a low voltage breaker and your amperage, in this case, let's say is 4,000 amps or higher, we don't have to worry about what that current is on the secondary side, because we're actually interrupting on the primary side. So yeah, we are sensing that current with those secondary CTs, and although let's say it's 5,000 amps, we're still only interrupting maybe a few hundred amps or 1,000 amps, whatever it is, on the primary side. So I'm not sure if that answers the question there.
I think that's a list of questions.
Okay.
Kyle, it's a very good job. We'll put together a Q&A list of all these questions and the answers that we can circulate. And your contact information is on the screen now. We do appreciate your participation.
Yeah, thanks for having me.
Thank you, everyone, for attending today. We'll talk to you in the near future. So long.